And this is what we'll use for the next week or so. I do. I have lots. You may have to sharpen it. So come on over. Oh, actually, it's pretty good shape. I'll do it. All right, cool. So you can see that that handout is hopefully a little smaller than the last one was, so that's good. I just want to make sure that I have mine because I wrote the stuff that we'll do over the next couple of days. So, questions at all about yesterday's stuff? Like we kind of like, you know, we started what? No, let's see if we'll see. We started here by just legging it, right? If we can just evaluate it by just dropping the number in, man, this is the easiest way to do it. And things worked out nice, right? I think it was like 1 over 2 pi, and then, you know, it worked out really nicely. This one, right, we had to mess around a little bit to be able to make it work for us by either factoring or using identities or doing something, right? And we have lots of skills with those, and I know that we're still kind of working through our Trig competency, and that's okay. And then we work through these things, right? Oh, let's the Pythagorean identities for like the first ones, or hey, look, sine over cosine or 1 over cosine, and let's just hold stuff in. If you want, and I'm not going to make you do it, but if you want, you can always go back and work through those problems now in these handouts. Now, if you have them, but hopefully they're sitting in your notes somewhere, that's fine. I'm not going to check any of those pages from it. Okay. And my plan moving forward, I apologize for not doing this, is to get you these copies before the day that we're going to work through them, not the day after. So I take full responsibility for that. So my bad. We looked at this because we ran to the issue of, okay, I get 0 over 0, so I know there's a hole, but I can't do anything about it. I can't like multiply by a conjugate, or I can't, like there's no binomials. I can't just you know, divide anything away. I can't write, you know, Pythagorean. I did like nothing. So the table was really nice. The graph backed that up, right? We saw how nice it was to be able to look at right here. So here I am on the left-hand side, sine of x over x. As we approach 0, where are we obviously headed? What y value getting close to? 1, yeah, right? The only problem is there's a hole. So there's got to be some kind of way to prove this, but it's not necessarily going to be the way that you see it. And so what I'm going to do with you, what I'm going to do to you, like what I'm going to do for you, is I'm going to show you the calculus style of where this comes from. Not because you have to recreate it, because you don't, ever. Okay? I'm never going to make you do it. I just want you to see why and how these kind of things came about, so that you can familiarize yourself with maybe a different style of how to deal with this, so that it's kind of different, a little new, and it's okay. Where's my buttons? There are my buttons. Okay. So, what I would rather you do, I don't want you to write this down. I really don't. I would rather you just experience it and just follow along as best you can. I will try to involve you. Don't peek yet. I will try to involve you as much as I possibly can so that you feel like you get it. Okay? But before I even do that proof, so remember what I'm trying to prove. Sine of theta over theta. Going to 0, right? The answer to that limit, guaranteed, is 1. Do we believe that from the table? Do we believe that from the graph? I want to prove it. Okay. Now to prove that to you first, I am going to show you the style of something super simple first. Maybe this you jot down in a super small space anywhere you are. Okay. It can be on a piece of paper. It can be in like an empty space, like the bottom of page 50. There's a lot of empty, like a little tiny like row of empty space. That's plenty of space. Because all I want you to do, so if you're at the bottom of page 50, like draw yourself a tiny little set of that. And as big as the space is. And this is only to kind of get you going as to why these limits that I'm gonna use a style of proof here that's just different. Okay, here's what I want you to do. Put a point like in the positive x-axis space, like kind of in the middle. Just put one. Wherever you want. And what I want to do is I want you to draw a super simple function that exists above the x-axis everywhere except at that point. So like above. Okay, cool, there we go. Something like that. So, and let's call that like f of x. And it can be even simpler than that. Like I give it like, I made it all smooth and rounded. So some weird polynomial thing. Cool. I'm just going to change colors for a bit. Now, I'm going to do the same kind of thing, but below the x-axis. So a whole function, whatever it looks like, I don't care, that exists below the x-axis, except like that. Follow you. And so let me ask you this. Do you agree that f of x is always greater than or equal, and I'm going to leave space intentionally here, but imagine just one long sentence. So way over here, do you believe that f of x is always greater than or equal to g of x in the space we got? It's always bigger, right? Except right here where they happen to be the same. Cool. Here's your task. Draw a function in between. Draw h of x so that it sits in between. Obviously, it's going to have to meet at 0 at that same point, right? So it's going to be in between. But draw some function that exists in the space in between. So f of x is always the big one, g of x is always the small one, h of x will always be in between. Anybody want to draw it on the board? You can use your fingers. Yeah, everyone. Here comes h of x. Beautiful. I like your feet. Thank you. So you did something like that, right? You drew it in between, and they all hit the same point, right? And so let's call this, like right here, let's call this point like some point C. And let me ask you this. What's the limit of f of x as x approaches C? Like, what's the y value? 0. Okay. What's the limit of g of x as x approaches? Zero, still 0. Okay, so f of x is always bigger than all of them. G of x is always smaller, but at some point they have the same limit. So without even looking, without even drawing h of x, what do you think the limit of h of x as x approaches c would have to be f of x is always bigger, g of x is always smaller, and h of x is in between. Gotta be 0, right? Here's what we just did. We took a function up here, a function down here, and we squeezed a function in between. I took these two and I sandwiched a function in between. This idea is literally, and this is not informal, it's called the squeeze theorem, or the sandwich theorem. That if you've got one function that's always big and one function that's always smaller, and you put one in between, it will always be in between. That's the idea. Weird. Why? Here's why. Here's where the fun starts. Drop your pencils when you're ready and just watch. Just experience. And be a part of it. I want to hear from you as much as I possibly can. Here's the limit. Remember what we're trying to do. The limit as theta goes to 0, sine of theta over theta is equal to 1. That's what I want to prove to you right now. Well, it's trig. I like drawing pictures. What is the best picture I can draw to help you understand trig? Unit circle. Ooh, a purple one. Nice. Okay, there it is. Let's give it some space. Let's let it exist somewhere. Oh gosh, that's a circle. I want a line. Line. Black line. Okay. There's sort of the y-axis, there's sort of the x-axis. Cool. Here's what I'm going to do. I'm just going to open up an angle. Okay, I'm just going to pick a theta, and let's pick it in the first quadrant and make a nice, I don't know, like, how about like right here? Okay, so that right there, that angle is theta. Now, what do I want to do, though? I want to let theta get smaller and smaller and smaller and smaller. So what's eventually going to happen is we're going to think about like moving that angle like down that way. I'm going to do that. I'm going to move it there. But this is not a one-sided limit. It's not just coming from the positive angles. It has to come from the negative side as well. So imagine it also like moving, like, so, all right, there's like another line right here. There's a positive theta and a negative theta, and they're just going to get closer and closer and closer. That's, remember, calculus happens in motion, so like imagine that motion happens. Cool? That's the plan. Now, if I could plug in 0, I think it's happy. But remember, sine of theta is the y value. Well, the y value right there, at 0 radians is 0. So 0 over 0, no. 0 over 0 should mean a whole, so I should be able to find that limit somehow. But algebra is not limited. At least not right away. Now, I am not the architect of this proof. Somebody way, way, way smarter than me did this already. So I'm just biting off all of their work, okay? I've watched this enough times to be able to recreate it for you. Okay, here's what I'm going to do. We are going to look at that line. So imagine it coming like right out of the origin, exactly perfect, right? And I'm just going to draw some shapes kind of buried within there so we can compare them. I'm going to draw a line that, imagine it went right through. Oh, man, I got it. It's got to be nice. Oh, wait. Oh, wait. There we go. I want to draw that triangle inside. See that one? That blue triangle? Okay. And I just want to think about it area. Okay. Well, what is the area of a triangle? Nice. 1/2 times base times height. Okay. Well, what is the length of this base if this is the unit circle? 1. Yay, unit circle. Radius 1. Okay, well, geez. What is this height? That's the height that we're looking for. I have no idea just by looking, right? It's not 1. It looks like a little bit less than 1. Well, let's think about it. Okay, so we opened up some angle of theta, and it took us up to this point right there. And that y distance, that length right there, is just whatever the y value is at that point. that make sense? Right? So this is some point, right, at xy, right there. And whatever that y value is, since I'm just coming up from the x-axis, is whatever that length of that is. Well, this is the unit circle. What is the y value at a point on the unit circle according to Trig? Say it again. Sine of theta. That is the length of the height. It's the y value at that spot. Now, remember though, it could be in the first quadrant up here where sine is positive, but it also could be down here in the second quadrant. The fourth quadrant where sine is negative. But this is area. I'm going to make it positive by saying absolute value. Okay? So here's our first area. The absolute value of sine of theta. 1/2 times 1 times the absolute value. So that is the area of that small blue triangle. Okay? Next area. Area of the wedge. That includes all of the triangle, but also like this part right here. All of that in there. That slice of piece. Figure out what that area is. Well, first, that slice included the triangle and the other piece, right? That little kind of weird arc spot in there. That's got to be more, right? That area has to be bigger, right? So this is less than or equal to the area of whatever that wedge is going to be. Does that make sense? Sizing? Okay, cool. So let's think about that area. Well, what's the area of a circle? I know, so much geometry. That boy, pi squared. But that's the whole circle. I don't want the whole thing. I just want a slice of it. I want to take a portion, a proportion of this circle. I don't want the whole trip around. I want the whole 2 pi thetas. I just want theta. I don't want to go all the way around. I only want to go this far, theta far, out of the 2 pi. That's how far I want to go. I want to take this section of this circle. Okay? Well, here we are in the unit circle. What's the radius? Yeah, I love 1. So nice. Okay, theta over 1. Let's make this nice and simple. Yeah. 1 times theta over 2. Now again, positive theta or negative theta. All right, I'll be careful. I'll put the absolute value just to be safe. Okay, so the area of that wedge, the absolute value of theta over 2. Theta, of course, in radians. Okay, all right. I see some nodding faces, makes me happy. Okay, last area. I'm going to raise a perpendicular from there. Make a big triangle. Which one? This one. I want that big triangle. Okay. Area of a triangle. 1/2 base times height. Okay. I got some space over here. I'm going to use it. Okay. So 1/2. The length of this base right there. All right, it's really only the height that's going to be true. All right, so think about that triangle. I just raised a perpendicular from the x-axis. What kind of angle is this right now? It's a 90-degree angle. That's the right angle. Right triangles allow us to use basic right triangle trigonometry. Now, the only thing that I know is I want to know this side right here. So, all right, so there's theta. So this side is the opposite side, right? I don't know the length of the hypotenuse. It's bigger than 1, but I have no idea what that is. But I do know the length of the adjacent side, right? That was just 1. Which trig function is opposite adjacent? Okay, so tangent of that theta right there is the length of the opposite side divided by the length of the adjacent side. Length of the adjacent side is what? Opposite over adjacent. Opposite over 1, just whatever that length. That height is tangent of theta. Opposite over adjacent, opposite over 1, there it is. And of course, he says absolute. So I've got 1/2 times 1 times tangent of theta. All right, so absolute value tangent of theta over 2. Okay. There's our double inequality. Feel good with that setup? Okay. Now, don't worry so much about all the triangles and wedges and stuff. Now we've got that double inequality to work with. Here comes the proof. I want to make things simpler for sure, but remember our end goal, that I want, really, like I'm trying to get to this. I want to see sine theta over theta somewhere. I want to get to that. All right, well, I got this whole dividing by 2 thing. I'm just going to multiply everything by 2. It's a double inequality. Multiplying by 2 makes everything twice as big and doesn't change anything about the actual inequalities themselves. So I get the absolute value of sine theta less than or equal to the absolute value of theta less than or equal to, all right, so tangent of theta. Again, this is not me thinking this. Somebody else thought of this. Let's call it sine over cosine. Okay, just to make it a little bit easier. Just get rid of tangent. I don't like it. I'm going to call it sine of theta, of course, absolute value, over absolute value. Good to there? Okay. Now we just mess with a little algebra. Try to get to that sine of theta over theta. Well, if I did it here, and like I chose to like divide by absolute value of theta, okay, well, ooh, sine of theta over theta, nice. Ugh. That would be 1, cool, that would be nice. But then, oh, yuck, that just got worse, right? I don't want to make things worse. I want to make things better. And so I'm going to do something in this step temporarily just to make things a little nice. I'm going to divide everywhere by the absolute value, not of theta, but of sine of theta. And you'll see why. Okay? So I'm going to divide by the absolute value of sine of theta. And we'll talk about what happens with the inequalities when we do that. Okay, divide by the absolute value of sine of theta. Here it comes. I'm going to divide by the absolute value of sine of theta. Multiply by 2. Okay. Why did I do that? Well, look what that is. 1. Right. Now, I'm dividing by something positive. Inequalities don't change. It's still less than. Okay. All right. Well, that is what it is. Fine. All right. It's like kind of what I like, but it's not exactly what I like. But we're getting closer. And then, okay, so those are gone. Sweet. Less than or equal to 1 over the absolute value. All right. Now, I was playing it safe with all these absolute values. Let's actually think about it. First quadrant, theta is positive, sine is positive. That result is positive. Fourth quadrant, like open up a negative angle. Negative and negative. Sine is negative down there. Negative divided by negative, still positive. These are no longer necessary because the result will always be positive. Except, of course, it's 0, but that's the problem anyway. Okay? Again, like we're stuck between like negative pi over 2 and pi over 2, first and fourth quadrant. To the right of 0, x is always positive. I don't need these. I don't have to worry about absolute value. Okay, so do we have exactly what's circled here somewhere? Well, what do we have? I know what you mean. Reciprocal. Yeah, we have the reciprocal. So let's take the reciprocal of everything. Now, can we do that with inequalities? Well, think about it. So here's an inequality that is true. 1 is greater than 1/2. Okay, take the reciprocal of both. Reciprocal of 1 is 1. Reciprocal of 1/2 is 2. Does the inequality stay greater than to be true? No, we have to flip it, right, to be true. So when we take the reciprocal right here, I'm just going to have to flip the inequality so that's true. But look, reciprocal of 1, 1. Okay, flip the inequality. There it is. Sine of theta over theta. It's reciprocal. Switch the sign. Okay, reciprocal of this. Finally, we got it. We got what we wanted, and it's included. Are we happy to there? Okay, because now what I'm going to do to give us some space, I'm going to come over here. Sine of theta over theta. I can just do that. What was the limit that we wanted to go to? Theta going to what? 0. Good. You know how like I multiplied by 2 everywhere and it was all good? You know how I took the reciprocal of everywhere and it was all good? It's had to like watch my signs. Let's take the limit everywhere. I'm going to take the limit of 1. That theta goes to 0. I'm going to take the limit of this and the limit of that. The limit of everything. Theta goes to 0 or 1. Theta right? The limit. Theta goes to 0. What we want, there it is. And I don't know what that is. I have no idea what that's going to be. And then theta equals to the limit. This theta goes to 0. Okay. Flashbacks to yesterday. I know, a long time ago. What's the limit of a constant no matter where we're going? I drew you this graph. I said, what's the limit? Like this is like the number 2. What's the limit as we go to -1? What's the limit as we go to 1? What's the limit as we go to 3? The constant, nothing changes, right? And because there's no place for me to put a theta, so how can the limit have anything to do with whether I'm going to 0 or going to pi? It doesn't matter. The limit is 1. Here's what I want. I don't know what it is. But look at that last one. What's the best plan for evaluating limits if I can do it? What's the easiest way to find a limit if it's defined and continuous? Log it in, right? Direct substitution. I have no problems going to 0 and just seeing what the cosine is. So let's do it. Go to 0 radians. What's the x value there? This limit is always greater than or equal to 1. Always. That limit is always less than or equal to 1. So what's that limit? Squeeze it. I trapped this function, this limit of it, between 2 constants. Had to be that value. Isn't that crazy? That's so cool. I just love that. Now, man, does that take a lot of work to get to? And I would never have thought of that on my head. Okay? And that took me, what time did class start at 1:10? That took me like 20-something minutes just to do that one proof. They kind of had me, you can do it in 10 and a half. So it's a little bit better. But that's what I did. I watched him do it. And he watched somebody else do it. And they watched somebody else. Okay? Standing on the shoulders of giants. But the idea behind this idea of being able to try to evaluate limits in a different way is just something I just wanted to introduce to you. Even if you could never recreate that on your own, it seems like you followed along pretty well to the logical thought process. And that's the nice thing about calculus, it is logical as often as possible to get to this. Okay? And so what we did yesterday, I'll go back to this just for a quick second, is down here at the bottom of page 50. So now if you're not there, get to that spot, but I think you're probably already there. Like we did this, right? We said, oh, there's that limit. Why? Because it was like 0.9999, 0.9999, 0.99. I was like, just like getting closer and closer and closer to 1. I cannot stress how important this limit is, how amazing it is. We're going to use it all the time. Best news, you never have to prove that limit. We just did. Now you know. Use it. Okay? And we're going to go looking for that limit. I want to like find that limit and isolate it. I want to use it. Okay? I like the table setup. It was cool. The graph was really nice, but the thing that backed that up with the proof was really, really cool too. The other one, turn to the next page. The other super important limit that we just can't find really quickly by direct substitution is this. So I just wanted to prove this one to you as well. This one's a lot faster. This one, I think you might even be able to like squeeze in up here or squeeze in down here if you wanted to. The thing about this limit and how we find it, I think you're going to really appreciate two of the things that I'm about to do as we move forward with these next couple of days. The strategies that I'm going to employ to find this limit. Now, I'm going to do it separately. So you can do it separately as well. But I want to find this limit, and what it does is I'm going to use that last one, the sine of theta over theta. I'm going to use that limit. If theta goes to 0, the value of that is 1, to help you prove this limit. And as I do this, you're going to see some ideas in how to evaluate trig limits that we just haven't done before. And so I think it would be good for you to write it down somewhere, wherever is convenient, where you ever have some space. It's going to take way less space than that one, right? Okay. A couple lines worth, that's it. Okay. We're going to find this limit. The limit, if theta goes to 0, of 1 minus cosine of theta. Okay. So wherever you want to do that, it's totally up to you. Not that you'll have to necessarily prove this limit to me again, but the strategies I'm going to use are going to be really helpful. Okay? I would love direct substitution, but nope, 0, 0. Right? This cosine of 0 is 1, 1 minus 1 is 0, 0, 0. Okay. So I got to do something. And I'm going to use a pretty nice and familiar little trick to algebraically manipulate this function. Let's multiply top and bottom by the same thing. Any ideas? What could be good for us to multiply by? Yes, the conjugate, man, love it. 1 plus cosine of 0. Multiplying by conjugate is always a good first idea. If you're not sure, what's it? Okay, cool. So I got to bring that limit notation with me for a while because I got some work to do. The whole idea in multiplying by the conjugate is to actually multiply out the conjugate part, right, the top part. So let's multiply out the top. The 1 times 1, okay, so that's 1. And we pick the conjugate always because we know those middle terms are going to cancel out, right? Plus cosine theta minus cosine theta, so I'm not even going to write them. And then minus cosine theta. And just like we have for the last couple of weeks, when we pick something to multiply by, we only multiply it in the space where we find it useful. But in the other space, we leave things factored in the hopes that something good can happen. All right, the limit again, and then we'll figure out what. All right. Do you see anything? And people at home, please, 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 I'd love to hear from you too if you got ideas. Anything about, like the top right there, that you recognize, that you notice, that may be worth trying? What do you think? What do you know? You guys tell me, which one? There it is. One, that top is sine squared theta. Beautiful. I'm going to leave the bottom. Love it. Good. Okay. Here's what's new. Here's a new strategy when dealing with limits. We know that sine theta over theta, that limit as theta approaches 0 is 1. And if I can isolate that sine of theta over theta and separate it from everything else, I can consider the limits separately. Here's what I mean. I'm going to rewrite this one fraction as 2. I'm going to break apart this fraction right here in a way that isolates the limit I already know. Sine of theta over theta. Because look at what's up top. It's just sine squared. I'm going to factor out a sine up top. What do I have left behind? Another sine. Right? Because when we multiply fractions, we just multiply top two. So sine and sine make sine squared. And so I'm going to factor out the kind of numerator that I like. Same thing with the bottom. I am going to factor out the kind of denominator that I like because I know this limit. Limit as theta approaches 0 of sine of theta over theta is 1. Gotta know. That limit is going to be so useful to me, and you'll see why here in a second. What do I have left? The 1 plus cosine theta. Okay. Now listen carefully. Once you finish writing. The limit of a product is the same thing as the product of those limits. I can separately consider the limit of this, the limit of this, and multiply those separate results together. Rather than considering the whole function all at once, I can consider the limit as theta goes to 0 of sine of theta over theta, and the limit of the second fraction, sine of theta over 1 plus cosine of theta, as theta goes to 0. So the limit of a product is the product of the separate limits. Okay. So if I can break a function into two fractions, or two things, do anything, being multiplied together, I can consider those limits separately and just multiply the result. And what's really nice about that first initial property of limits is that it works for addition. The limit of a sum is the sum of the limits. Just consider each part separately and add them all up. Works with subtraction. You have two things being subtracted, you want the limit of all of it, take the limit of the first thing, limit of the second thing, subtract. Addition, subtraction, multiplication, division, all works. You've got these properties that allow us to break them apart. Now, why? Like, what's the point? Well, look at that first thing. There it is. That is 1. So we might not be able to divide the problem away, but if we can go searching for this limit, and I'm about to prove to you the second one, right? 1 minus cosine theta over theta. We go searching for those two limits by looking for them buried as fractions, like pull them out, or being added or subtracted. And we have 2 full days, Thursday and Friday, we're going to practice these ideas, okay? Lots of time to work with, okay? Now I can just worry about, like, all right, boom, there it is, there's 1. That's the limit, and I know it, and I can use it, and you never have to prove it to me. I just have to go looking for it. Now I can just evaluate that limit separately. Why is that useful? Plugging in 0 does not cause any problems, right? Plugging in 0, okay, so sine of 0 over 1 plus cosine of 0, 1 times whatever those are. Right? Sine of 0 is 0. Cosine of 0, 1. Okay, so 1 times 0 over 2, 1 times 0. So here's the big takeaway. we've got these two limits, right? The limit as sine of theta over theta as theta approaches 0, that's 1. This one, we just proved it. The limit as theta approaches 0 of 1 minus cosine theta over theta, that's 0. And those two limits need to get stuck in your brain forever. These two are the two trig limits you have to do. They are super, super, super. Because those are the limits we're always going to go searching for. I'm going to look for sine theta over theta. I'm going to look for 1 minus cosine theta over theta. I'm going to pull it out. And I don't care if I pull it out with like factoring or I just got two fractions being added or subtracted. I will just separate them and I will consider their limits separated. And that idea that the limit of a product is the product of limits, that the limit of a sum is the sum of limits, that the limit of a difference is the difference in limits, so helpful when we get to chapter 2. I keep saying that. We actually start using these limits to worry about like what's happening at functions. Okay, and so you've got a spot for it. I think everybody's written down everything they need to. I can always go back, but I just want to hop on here real quick. Right, bottom of page 51. In case you were working somewhere else, there's that one. So if you wrote it somewhere else, you want to have it in a spot where you can go find it. Bottom of page 51, there is that second limit that you need to know. So much so that probably when we get to this chapter 1 test next week sometime, right? Because we'll take today, we did it, yay. Tomorrow and Friday, just try this stuff out. Okay? We'll take Monday to wrap up kind of just a last final idea. Tuesday review for sure. Maybe even Wednesday if things kind of trickle in that direction, and then Thursday test. So I don't know. I haven't figured it out yet. I don't know if I want to do like just an in-class part, or just an at-home part, or a combination of the two. I have to figure out what that looks like in terms of how much I want to give you. Like I don't want to give you too much all at once. I don't want to give you a 6-page test and say here's 50 minutes to do it. That's not good. But I need you to start getting into the habit of doing things here as well, just so that you can get the, like study for a math test and also. But that's what I want to be able to do. Now, I want to do this really quick. So turn the page now. We're there. We did it. Yay. Now we can start practicing. What you're going to see, I put this up on Canvas. Homework 1.5 that is not due until Friday are the next 5 pages of practice. We're going to have plenty of class time to work on it. I hope that class time will be enough to get it all done. Okay? Because remember, you guys you guys are here Friday. You have school on Friday. So, but I want to skip down to number 5 to start. So I just want to show you how this process kind of plays out. And we have 2.5 minutes to see if we can do it. So page 52, bottom page 52, number 5. Let's give it a shot. Remember what we're searching for when we get to sine of theta or 1 minus theta. Okay? Because I would love to just plug in 0, but I'll be divided by 0, and so that's not good. So let's think about how we can rewrite this to try to solve. What do you think? What would be a good potential first step given a set of tangent of theta over 3? Any good ideas to start? I like it. Let's turn tangents into sine over 3. Right? Thinking about like identities from pre-calc, we talked a little bit about, right? If it's squared, try a Pythagorean one. If it's not, try changing everything to sine, cosine. Okay, complex fraction, yeah. Let's get rid of the complex part by putting stuff together. A fraction divided by something goes into the denominator. Sine of theta over theta cosine theta. All right, nothing to cancel, nothing to divide away, right? No conjugates because there's no binomials. Now is the time when you start searching for one of those two limits. When you see sine of theta over theta, or 1 minus cosine of theta over theta, kind of buried somewhere. There's sine of theta over theta. Give me like 30 seconds. Pull it out. We're just not going to factor it out and create two fractions. That wouldn't, if we did multiply them back together, we'd get that one. Of course, that's not the idea. I want to break them apart on purpose so I can break them apart. Well, I pulled the sine of theta out from the top, so I just have a 1 left behind, right? There's nothing there. But the denominator goes on. The whole point of doing that is to turn one limit into two. So I want to see that step where you kind of break things apart, but now what we'll have is we'll have two things being multiplied together. The limit of the first fraction, sine of theta over theta, times the limit of the second one, 1 over cosine. What's that first limit? That should be the problem, right? That's us getting rid of the problem by kind of isolating that one or the other trig limit and then going for it. How should we evaluate the other one? Plug it in. 1 over cosine of 0. 1 times 1 over cosine of 0 is 1. That's the idea. Okay. We have 2 days to get better at that. Okay. Bring us back with you tomorrow. I will. I'll send you a homeroom. Right. Don't forget to go to the homeroom. You guys at home are all set. Thank you guys for coming and hanging out. I will see you in class tomorrow. Stick around if you have any questions.